Dear students, continuing with our lecture series on oxidation reactions, in this lecture we will discuss how lead tetraacetate can be used as a reagent for different types of oxidation reactions in organic chemistry. Lead tetraacetate is a very powerful oxidizing agent, and few disadvantages is that it is hygroscopic and very toxic in nature, and because of the hygroscopic nature it turns brown on exposure to air due to formation of lead dioxide. So this will limit the oxidizing capability of lead tetraacetate because of the formation of this lead dioxide. Then this lead tetraacetate that can be prepared if we heat red lead oxide Pb3O4 in a mixture of acetic acid and acetic anhydride approximately at 70 degrees centigrade. And this lead tetraacetate formed by this method can be recrystallized from acetic acid to give white crystals, which can be used directly as the oxidizing agent. The important functional group transformations which take place using lead tetraacetate, that is oxidation of alcohols, cyclization of saturated alcohols, then reaction of carboxylic acid with lead tetraacetate to give us different types of oxidation products. Then lead tetraacetate can also lead to acetoxylation of different types of organic compounds, and then it can also undertake dehydrogenation of different types of organic compounds. So first is reactions with alcohols. Uh, the lead tetraacetate in presence of pyridine at room temperature can convert primary alcohols into aldehydes and secondary alcohols into ketones. And the advantage of using LTA in these types of reactions is that the final product is aldehyde or ketone. No further oxidation to carboxylic acid takes place. So this is the main advantage of using lead tetraacetate. So these are two of the common examples. This is pentanol. This is oxidized to pentanal in 70% yield when lead tetraacetate and pyridine they are used at room temperature. Similarly, this allylic alcohol, that is cineamyl alcohol, is oxidized to cinnamaldehyde in 91% yield using lead tetraacetate and pyridine. Similarly, 1,2-diols, they can undergo oxidative cleavage of the carbon-carbon double bond to give us carbonyl compounds like aldehydes or ketones, or both aldehyde and ketones they can be formed depending upon that what is the structure of the diol, what is this R1 and what is this R. If this R is H, then we will get an aldehyde, and if this is an alkyl, we will get a ketone. So an aldehyde from this part, a ketone from this part. So we can either get two aldehydes, two ketones, or a mixture of aldehyde and ketone through oxidative cleavage of the glycol using lead tetraacetate. And here it has been found that cis-1,2-diols they are more reactive as compared to trans-1,2-diol. So which clearly says that in the oxidative cleavage methodology or the mechanism, there must be a formation of a symmetrical intermediate which can be easily formed from cis-1,2-diol. Similarly, the commonly used solvents, they are benzene, toluene, dichloromethane, and tetrahydropurane. These are the most commonly used solvent for the oxidation reactions of alcohols or diols. And when three or more hydroxyl groups they are present on the adjacent carbon, then the middle hydroxyl group is converted into formic acid. So this, as I have told you, 1,2-diglycol, this will cleave from the center of this carbon-carbon bond, and we will get 2 carbonyl. That's the product. So these are few examples. This is trans 1,2-diol, and in presence of lead tetraacetate, sodium carbonate, dichloromethane at very low temperature of the order of minus 40 degrees centigrade. This will undergo oxidative cleavage at this carbon-carbon bond. This will produce a formaldehyde from here, and this will give us the aldehydic oxidation of this hydroxyl. So one molecule of formaldehyde and this aldehyde will be formed by oxidative cleavage of this carbon-carbon bond. Similarly, in this molecule, this is cis-1,2-diol, and in presence of lead tetraacetate in acetic acid and benzene as solvent, this carbon-carbon carbon-carbon bond will undergo cleavage at this point. This will lead to the oxidative cleavage for the formation of aldehydic group. Because here methyl group is attached, this will be oxidized to ketone. So aldehydic functional group and a ketone functional group is formed by oxidative cleavage of this carbon-carbon bond. Now, as far as mechanism is concerned, as I have told you that cis diols, they are more reactive in comparison to trans diols. So, some different mechanisms they have been proposed. So, you can see the conformation of this molecule here. Both the hydroxyl groups, they are diaxial, and the rate of reaction, if in this case, is 1 for the cleavage of this carbon-carbon bond, whereas in this diol where conformation one hydroxyl group is equatorial and other is axial, the cleavage of this bond, the reaction is 1000 times faster than in this conformation. So this is because in this molecule there is a favorable orientation of the hydroxyl group for the formation of a for the formation of an intermediate with lead tetraacetate, whereas formation of intermediate with lead tetraacetate in this case is less as compared to this one. That is why rate of reaction in this case is far more as compared to this one. Now, there are two main mechanisms which have been proposed. In the first mechanism, the lead tetraacetate reacts with 1,2-diol, where both the hydroxyl groups they interact with the lead tetraacetate with the removal of H from here, acetate from here, one molecule of acetic acid, similarly H from here, and acetate ion from here, two molecules of acetic acid. They are removed to, for the formation of this type of a symmetrical lead acetate intermediate with a 1,2-glycol. And then this symmetrical intermediate undergoes oxidative cleavage of this carbon-carbon bond in this way that two carbonyl compounds they are formed with the elimination of lead diacetate as a as another product of this reaction oxidatively. So we will get the corresponding carbonyl compounds and lead diacetate. In the second mechanism is that only one hydroxyl group, if these hydroxyl groups they are trans, here both the groups they were cis, so that is why there was an easy formation of the symmetrical cyclic intermediate. Whereas when the hydroxyl groups they are trans, then only one of the hydroxyl group will react with lead tetraacetate to get with the removal of one acetic acid molecule to give us this type of intermediate. And then the hydrogen from the other hydroxyl group is lost with the oxidative cleavage of this bond, and one more molecule of acetic acid is removed to give us the products like this. So you can see that here a symmetrical intermediate is formed, and the intramolecular cleavage, oxidative cleavage, will lead to the formation of this. So because here uh, in the single step these can be converted into this, and here two steps are required: first this formation of this, then removal of this, and that is why this is a faster process, whereas this is a slower process. Then if one of the hydroxyl group is replaced by say amino group, beta amino alcohols, or 1,2-diamines, or alpha hydroxy carbonyl compounds, or 1,2-dicarbonyl compounds. They also react with lead tetraacetate, and on similar mechanism, the cleavage of this bond will take place to give us similar dicarbonyl compounds they are formed. So when cleavage of this is take place, this will give us aldehyde, whereas this will give us uh, first ketone, and then on reaction with ethanol, this will be converted to an ester. Then if we are having saturated alcohols which have gamma hydrogen present in the molecule, then those types of saturated alcohols, they will undergo cyclization in presence of lead tetraacetate to give us a cyclic heterocyclic compounds. So for example, this alcohol butanol having gamma hydrogen will undergo cyclization with the hydroxyl group to give us tetrahydropurine as the product. Similarly, this cyclooctanol having gamma hydrogen will undergo cyclization to give us this type of ether. Then for this molecule here also, this is a saturated alcohol where we are having gamma hydrogen present at this place. So this will undergo cyclization to give us these types of structures. We can see over here that only saturated hydroxyl group will undergo cyclization, and there is no effect on the carbonyl group of the. Now, as far as mechanism of these reactions where gamma hydrogens they are present is like this, that in the first step the saturated alcohol will react with lead tetraacetate H from here and acetate ion from here. One molecule of acetic acid will be removed, and this lead triacetate will get joined to this oxygen, and then either when this is heated or under UV light, this will be cleaved, lead oxygen bond will be cleaved, and we will get this type of alkoxy radical formed with the removal of lead triacetate radical from here. And then this alkoxy free radical will undergo transfer of this H radical from here to this oxygen, and alkoxy free radical will be converted into an alkyl free radical, and this alkyl free radical will then interact with the lead triacetate radical formed in this step, and we will get this type of lead 3 alkyl compound formed during the reaction. And then this will undergo removal of lead diacetate and acetate ion from here with the formation of this type of carbocation. And then this carbocation will undergo cyclization to give us tetrahydropurane as the product. So this is how saturated alcohols, they react with lead tetraacetate to give us cyclic compounds or tetrahydropurane in this particular case. Then carboxylic acids, they also react with lead tetraacetate and they undergo decarboxylation of this carboxylic acid group to form unsaturated compounds. So this cyclobutane carboxylic acid will give us cyclobutene as the product when lead tetraacetate is used as an oxidant. Similarly, these dicarboxylic acids, they will undergo decarboxylation at both the points with the formation of a carbon-carbon. So 1,4-cyclohexadiene will be formed as the product. Similarly, in this case, when we are having lactones, they are formed when there is a carbon-carbon double bond near to the carboxylic acid. So this will undergo cyclization at the carbon-carbon double bond to give us these types of lactones as the products. Then lead tetraacetate can also lead to acetoxylation of different types of carbonyl compounds or benzene derivatives. So for example, if we are having this molecule ethyl methyl ketone, and when this is reacted with lead tetraacetate, then this will undergo acetylation at the alpha position of the carbonyl, and we will get this type of alpha acetoketones as the product. Similarly, cyclohexanone, this is a symmetrical ketone, so either at this alpha position or at this alpha position it can undergo acetoxylation to give us these types of uh, products where acetate group is attached at the position alpha to the carbonyl. Then benzene derivatives like naphthalene or toluene, they also undergo acetoxylation on reaction with lead tetraacetate and acetic acid as the salt. So, for example, naphthalene is oxidized to 1-acetoxy naphthalene when lead tetraacetate is used in presence of acetic acid. Similarly, this toluene, this undergo acetoxylation at the bacylic carbon hydrogen bond to give us these types of acetoxylation products. Then amines, aliphatic amines on reaction with lead tetraacetate, they give nitriles through dehydrogenation reactions. So dehydrogenation at this carbon nitrogen bond will take place, and two molecules of hydrogen gas, they are removed by lead tetraacetate to give us nitriles as the product. Similarly, these types of biphenylic phenols, they also undergo oxidation to give us diphenocquinones as the derivatives. So hydrogen from here and here, they will give us different types of diphenocquinone products. So these are the references which have been used for this reaction, this lecture. Thank you very much.